Hello everyone, it's Peter here. I'm going to go through the physics mock exam for double and triple. So this is the 1 hour 30-minute test that you did. Going to go through the questions one by one. I'm in the science department at the moment, so there might be a few interruptions. Sorry about that. Here is the first question, and it's about a velocity time graph, and you need to know these points about a velocity time graph. The first is that the constant velocity on a velocity time graph is going to be shown by the fact that the velocity is not changing, the flat part here. If the velocity there is a specific value, let's say it's 10 meters per second, you can see that along this whole entire stretch, it doesn't change. So the horizontal part of the line is the first mark. Distance travelled is shown by the area under the line, because the distance travelled is the same as speed times time. Let's just take this area here from this time here to this time there. Well, the distance travelled is velocity times time, or speed times time, and that's the same as imagining you had a square here or a rectangle here. You're measuring the height times the width. That's the same as doing velocity times time. The area under it gives you the distance. Average velocity is given by the total distance divided by the total time, b. That's just checking that you know speed equals distance over time, and that velocity is the same as speed, except it's also got direction. Question 2 is about a nuclear reactor, and this question was actually taken from a much larger question, but we simplified it to just look at one section, which was what controlled nuclear fission means. And it's a 3-mark question. So the things that you could have said are: each fission is caused by a single neutron. So a neutron, you could say a neutron goes into or hits a nucleus, and that would have got you the first mark. And if you did a small diagram like this, a neutron goes into a nucleus and gives out more neutrons, then you're showing that more neutrons are being released. That would have got you the second mark. If you said something about this releases energy, then that would have got you the 4th mark. You could also say for marking point 5 and 6 that control rods are used to control the reaction. The question is actually about controlling a nuclear fission reaction. So control rods absorb neutrons, and that means that when you put them down, all of the neutrons are being absorbed, and less can actually cause a fission to happen. If the control rods are lifted up, then that will allow more neutrons to hit more atoms of uranium, causing more fission to happen. So this is all about nuclear fission, and that would have got you 3 marks. Question 3. So this question is all about waves. Which of these properties are the same for all electromagnetic waves? The speed in free space is always the speed of light. Okay, they all travel at the speed of light. Everything else can change. So draw a line linking these types of electromagnetic radiation with its uses. In my class, I think everyone got this right. So X-rays are for broken bones, microwaves heat food, and gamma rays for medical traces. It's all fine. And the next question, electromagnetic waves are transverse waves. Describe how the vibrations relate to the direction of the wave. Well, transverse waves are these squiggly ones like this. So the wave goes in this direction, but the vibrations move up and down. So if you said vibrations go up and down and the wave moves in this direction, you would have got a mark. If you're going to say it in words, you had to say that the direction of vibration is perpendicular to the direction in which the wave travels. And the next part of the question, Another type of wave is used in hospitals, ultrasound. Ultrasound is used to make images of internal organs. A scanner emits an ultrasound wave and records any reflections. The frequency of the ultrasound waves is outside normal human hearing. So which of those could be the frequency of an ultrasound wave? You need to know that human hearing is 20 hertz at the bottom end to around about 20,000 hertz at the upper end. 20,000 hertz is the same as 20 kilohertz, so the only option that's higher than 20 kilohertz is D. You need to know that ultrasound is above normal human hearing, and it's 20 kilohertz. So the scanner records the time taken for when a wave is emitted to when its reflection is received. And you've got this equation and you've got to explain why have you got this half value. So the depth of, so let's actually draw a diagram here. So imagine you've got an object here and you've got your scanner at the top. This is something inside a patient, and you've got your scanner at the top, and it's going to send out an ultrasound wave and it's going to hit an object, and that is going to be reflected and it's going to come back. And the equation you see here, depth is a distance, speed and time. This is actually just a rearrangement of the speed equals distance over time equation. So if I write down distance equals speed times time, well, the distance, that means the distance that the wave travels, and that's, okay, so the distance that the wave travels is there and there, equals the speed of the wave multiplied by the time it takes for the wave to go from here to here. And that equation is correct. So why is the half used? Well, because you're only trying to find out the depth. You're not trying to work out the distance in and out. You're only trying to work out the distance just there to the actual object. And you can see that green arrow is half the distance of the actual wave that the wave travels. The wave travels in and out, and the ray you're only trying to find out the distance one way, going in. So if you did a diagram like that with a little bit of explanation, then you've got the mark. It says here in the mark scheme, wave travels there and back. So, and depth is half of the total distance travelled. But a diagram can really, really help. So something like that will actually pretty much get you 2 marks. I think if you do that diagram, it makes sense what's going on here. Here, for part 3, an ultrasound wave travels faster in the patient than it does in air. So how can a change in speed affect the wavelength of an ultrasound wave? So how does change in speed affect the wavelength of an ultrasound wave? You need to be thinking about refraction. That's a good idea at the moment, because you're talking about something going from one medium, a wave going from one medium, the patient, to another medium, the air. So it travels, imagine this is a boundary, you've got air here, and you've got patient here. You end up with the waves going at one speed in the air and another speed in the patient. So let's say in the air, the waves are kind of moving along quite slowly, and in the patient they speed up and they move a lot faster. So what happens is if the waves are going faster, this is to do with the fact that this is because the wavelength has actually got bigger. So the wavelength increases. Another way to think about this is that frequency doesn't change. Frequency doesn't change, and we know that the speed of waves equals the frequency times wavelength. So if the speed increases, either the frequency or the wavelength increases. The frequency of light is related to the colour of light, and when light goes from air to glass, it doesn't change colour. It stays the same colour. The frequency doesn't change. The wavelength is what would change. So the speed increases because the wavelength increases is the answer for the question. Is the answer to the question. So the next part, question 4, is about electricity. So question 4, here we have to add a voltmeter to measure the voltage across the LDR. So this, the LDR is the light dependent resistor, and the light dependent resistor has light going into it. And sometimes you see the diagram for an LDR looking a little bit like this. This is a resistor, so it's already got a resistor box around it. Light goes in, and sometimes you have a circle around it as well. We can see here that the LDR is this component at the top. Voltage can be measured by putting a voltmeter across it like that. And that would have got you the 2 marks. 1 mark for putting the voltmeter in parallel, because a voltmeter doesn't go into the circuit like that. That's not how you would do a voltmeter. And another mark for getting it around the LDR. So how can a student work out the resistance of the LDR using this circuit? Well, you need to know V equals IR. So voltage equals current times resistance. Resistance equals voltage divided by current. And then you'd need to say measure the voltage using the voltmeter, measure the current using the ammeter. And so let me have a quick look on here. That's the wrong question. The reason you're seeing question 4 on the right hand side is because we took out a question for this particular test. So here, voltmeter connects in parallel, the current reading and the voltage reading, there you go. R equals V over I. So there you go, R equals V over I. That will get you 2 marks, but you need to probably say from voltmeter, from a voltmeter, and this is from ammeter. And let me spell properly, from ammeter. So the next part of the question is part B. Student shines light on the LDR through a circular hole. And what you've got to do is look at this experiment and know what an independent variable is, what a controlled variable is. What are we changing? Well, we're changing the diameter of the hole. That's what keeps on changing, different diameters. The control variable in this experiment is, well, the distance from the card to the LDR. It's always 5 centimeters. It's always 5 centimeters. The control variable is the one that doesn't change. Part 3, the photograph shows how the student placing a metal ruler to measure the diameter of the hole. Suggest how the student can improve this technique using the same ruler. Well, you could just move the ruler so that the ruler is over the hole instead of just further away from it, because otherwise you'd have to use a set square. So actually you could say use a set square. That might work, so that you're definitely lining up and you definitely know that those values, those angles are right angles. Or you could say move the ruler over the hole. Okay, move the ruler over the hole. It says here draw guidelines. Yeah, those are all okay for 1 mark. Part C. You have to plot a graph for part C, if I remember. So instead of plotting the graph, I'm just going to go through what you need for 4 marks, and you should know this. You get 1 mark for making sure that you've chosen suitable scales. Go up in 1s, 2s, 5s, or multiples of 10s. Those go up in 10s, go up in 20s, go up in 50s. So if you look at this, whoops, gone back too far. We've got diameter that goes from 8 to 30, and the LDR goes up to about beyond 1,000. So 8 to 30. So this has to go from about 8 to 30, and this is going to go from about 0 to 1100. So 8 to 30, well, that would be 0, 5, 10, 15, 20, 30. Sorry, 5, 10, 15, 20, 25, 30 there. And this would go up in, that would be 200 through 400, 600, 800, 1000, 1200 would fit that range of values from 0 to 1100. That would be fit there. This would fit there. Labeling the axes, so you've got here distance, and that should be resistance. Include units, so millimeters, ohms. plotting points. If you plot the points correctly, you get 2 marks. The next part is a curve of best fit. And just to point out a few things, imagine you had a couple of points like this. Okay, I'm just going to do it for these points. If you decided that what you were going to do was do a line to join up that point to that point and that point to that point, you wouldn't get the marks. And it says here, reject dot to dot. This is why I keep on saying, and I know your other science teachers keep on saying, never do this. There is never a situation where you're going to get marks from that, and people are still doing it. So a curve of best fit that tries to go through as many points. It doesn't actually matter if you don't hit the points exactly, but it tries to go through as many points as possible. So describe the relationship between the resistance of the LDR and the diameter of the hole. 1 mark for saying, as you increase the diameter, you decrease the resistance. Increase diameter, decrease resistance. And the second mark is for saying something about the fact that it's actually a curve. So something about a curve, you have to say, essentially it's non-linear. It's some kind of curve. So if you said something like, the bigger the diameter, the lower the resistance, would be okay for the first mark, and for the second mark, it's non-linear. You could even go into more detail by saying that, actually giving some values here. So from 5 to 10 millimeters, the drop was this much, and from 25 to 30, the drop was only this much less. So you're giving a bit of numbers here. That completely rounds off to make sure you definitely got all the marks.